Okay, so hello everyone. I'm Norman Wildberger. We're here at the University of New South Wales. Today we're going to have a little tutorial session where we are going to look a little bit in some detail at this example that we were looking at last time. Essentially a surface created from the folium of Descartes. And what we'll do is we'll use GeoGebra to try to see if we can get some kind of visual understanding of tangent planes and tangent conics to this cubic surface. So it'll be a chance for us to practice some GeoGebra skills as well. All right, so let me remind you briefly what the story was from last time. So we have this polynomial of x and y. It defines a surface in three-dimensional space, x cubed plus y cubed plus 3xy. And we're looking at that surface above a fixed point rs in the plane. And then what we did is we expanded things out, and we got this basic formula, basically an expansion of the polynomial in terms of powers of x minus r and y minus s. Okay, this is basically following Lagrange. And now what we're going to do is we're going to interpret the initial parts of this polynomial as tangent objects to the surface. So the linear terms, these first three ones, form the tangent plane. And I've rewritten them or made it a little bit short by expanding these things out, so it's just a expression in linear expression in x and y. So that's the first Taylor polynomial to the surface. And then the second one is obtained by going all the way up to the quadratic terms, just ignoring the cubic ones. So this plus this plus this plus this plus this plus this. And that turns out to be this if we write it all out. And another way of writing down what it is it's really just the difference between the polynomial that we started with and these cubic terms. So another way of writing it down would be to write down the polynomial and just subtract these two cubic terms. Okay. So what we are planning to do is we want to visualize this surface, and we want to see what do the tangent planes look like, what do the tangent conics look like. Okay, so here we have GeoGebra up and running, and let's see if we can illustrate some of the things that we're talking about here. All right, so first what we want to do is we want to exhibit the surface itself. Now we only have a two-dimensional scene to play with here, so what we're going to do is we're going to input level curves for the surface. And what we'll do is I'll write down x cubed plus y cubed plus 3xy down here as the input, and let's say equals 0. And before I do that, I'm going to copy that. Okay, I've copied that, and I'm just going to press enter, and we see the curve itself, the original folium of Descartes. That's the zero level curve for this surface. Okay, we can now, I'm just going to copy that again and replace the 0 now with, say, minus 1. We get that. And maybe with minus 2. And maybe with minus 3. All right, there we have a few different versions on that side. And then on the other side, with 1, just a line. With 2, maybe with 3. And I'm going to also do with a value half. Okay, with the value half, which is the last one, you see that there is a little bit in the middle there too. So what we have here now, these are level curves. What we see is that the surface, if we're thinking about looking down on the surface, okay, we're looking down on the surface, then the surface is going up in this direction. It's rather, right here, goes up very steeply. Okay, it's going up in this direction, and down in this direction, it's going down. Around the origin there's a little hill. So that little ellipse there is a little hill that's sticking up, that's at level 1/2. The maximum that that hill gets to is height 1. Just touches height 1, so you don't actually see the point. That's actually part of the line when the thing equals 1. All right, so that's the curve there itself. And now let's see if we can draw some tangent planes. So to do that, I'm going to create a point, and I'm going to illustrate this slider tool here, which is quite useful. So what we have is a slider. If I press this slider, I'm going to get, and click here, I get a slider, and let's give it the name R. Okay, and we won't worry about the domain right now. So there's a slider. This thing here has value R. If I move it around, it goes from -5 to 5 in, as it turns out, 0.1 increments. And I can move this wherever I want. Maybe I'll put it over here so it's out of the way. Then I want another slider. And put it here, and it'll be called S. And I might see if I can rotate that. Horizontal, vertical. Okay, it's now a vertical one. All right. It's also going from, I guess, -5 to 5. All right, now I'm going to, down here, make a point with coordinates R and S. And I'll probably give that a different color so you can see it a little bit better. Let's color it, say blue. Okay, there's the point. And it's now, its x-coordinate is controlled by this slider, going from -5 to 5. And its y-coordinate is controlled by this slider. If I just grab A itself, can I move it around? Oh, yes, I can. It's even better. I can move A around now directly, and the two slider positions automatically move around to record the x and y coordinates. All right, so that point has coordinates R and S now. And what I want to do is I want to try to illustrate the tangent plane that lies over this point. Okay, so how am I going to do that? Well, I'm going to, it's a plane. We're going to try to show its level curves as well. All right, so what we're going to do is we're going to use the formula for our tangent plane, which is right here. And I'm going to input that, and I'm going to set it equal to, say, 0 and perhaps 1. Okay, so from the board, I have -2 R cubed minus 2s cubed minus 3rs, and then plus 3 times r squared plus s times x plus 3 times s squared plus r times y. All right, so that's the equation for the tangent plane. It's a function of x and y, and we're going to set it equal to something. Let's set it equal to 0. But before I do that, I'm going to copy this because I'm about to do it again. All right, so there it is there, and now let's see what that actually looks like. I'm going to enter that. Okay, that's a line. That's the line where the tangent plane meets our coordinate axis, the xy plane. Let's give that a color. Oh, let's put it somewhere in the middle of the color spectrum, say green, because it's around 0. Okay, now I want to also, at that same curve, let's just make sure that I have it right, minus 2r cubed minus 2s cubed minus 3rs plus 3r squared plus s times x plus 3s squared plus r times y. Okay, now I'm going to have it equaling 1, say. Okay, that's pretty close to that. Let's see if that's just because of... Okay, so let's give this a second one a color. A little bit further up in the scale, maybe orange. Okay, so the orange one is the place where the tangent plane is equal to 1. The green line is the place where the tangent plane is equal to 0. And so I hope you can visualize this tangent plane. Okay, it's coming out at us. It's lying in the plane of the board on that green line, and then it's coming out, and it has height 1 on the orange line. So it's a plane like this. So what's that telling us? Is that telling us that at that point A right there, this hill is, well, if we're looking down, it's sort of slanted this way. It is actually a hill. Let's go around that hill. Let's make sure we believe that. So if we go around the hill, we're going around the hill, you can see the green is lower and the orange is higher. And if we go out here, well, the same kind of phenomena is, but the things are getting steeper. The two lines getting closer means that they're getting steeper. And here here you can see here that they're facing the other way. Here there's the green on this side and the orange on this side, so the hill is, the tangent plane is facing this direction. It's going up in this direction here. Okay, so that's good. Now let's try to get the tangent conic. So we have to take one of these two equations and input it and see what the different values are. All right, so let's do the first one since it's slightly simpler. X cubed plus y cubed plus 3xy, and then we have to subtract x minus r all cubed, and we also have to subtract y minus s all cubed. Okay, and let's set that equal to 0. Before I do that, I'll copy it. Okay, so now I'm going to enter that, and I don't see anything. Oh, now I see something. So here, let's have a look at this thing. Object properties. That was 0, so I'm going to call it green. And I'm also going to make it a little bit thicker so we can see it better. We're interested in that. Okay, so that's part of the level. That's a level curve for the tangent conic at this point A. It's the 0 level curve. All right, now let's do the same thing. Instead of replacing, we'll replace the 0 with a 1. See what we get? We get another curve. And we will also make it thicker and color it. That's higher up, so we'll make it orange. How about something a little bit further down below? So V maybe minus 1. Maybe blue. And maybe I'll do another one even further down, say minus 3. Oh, now we get something in the different direction. And we'll make it ultraviolet, or violet, say. All right, so let's see if we can blow this up a little bit so you can see it a little bit better. Okay, so what do we have here? So this is the point A, and what we have here is a description of some kind of visualization of the tangent conic to the surface at the point A. So what kind of a surface is this? Well, you see the level curves are hyperbolas. And as we go up, they're hyperbolas that are going in this direction. So if I was sort of putting my hands over the surface from on top, it would be coming out, going up like this in this direction. From the blue to the green to the orange, that's going up. On the other hand, in the other direction, it's going down. So it's a saddle shape, a bit like the crook of your hand here. In one direction, it's going up. In the other direction, it's going down. Okay, and so that violet one that we see, that's further down. That's showing us that the thing is going down in that direction. So this is actually a quadric, which is, well, you don't see something like this in one dimension. It's a phenomena that appears only in two dimensions, where the quadrics become simply more interesting than just parabolas. In one dimension, a quadratic function is just a parabola, and it's relatively the same. But here, there's this possibility here. So let's have a vary of the point A and see what happens to things. Well, let's get closer to. Oh, now something we see. Now see something now different has happened. When we're here, the nature of this tangent conic has changed quite dramatically. Now we see the level curves, which are all ellipses. That means it's actually an analog of a parabola. It's what's called an elliptic paraboloid, opening downwards in both directions, but by unequal amounts in the different directions. All right, so I remind you, the orange is up at the top, orange is high, and then green is at 0, blue is at -1, and violet's at -3 or something like that. All right, so we can move this thing around. Well, over here, still we have a saddle-shaped kind of quadric. And at this stage here, we get that elliptic kind of quadric. So how can we tell what kind of quadric we're having? Well, I'm not sure if you can see here in the dark, but here is the equation for the tangent conic. And the higher degree terms are 3rx squared, 3sy squared, and 3xy. Those are the quadratic terms, and then we have some linear terms in x and y. Now we're going to be talking about quadrics more, but I think probably you know from advanced calculus that if you have a quadric like this, the nature of the quadric is determined by these top entries. And in fact, if we factor out the 3, we're really talking about r times x squared plus, say, xy plus s times y squared. And perhaps you remember from calculus that in order to analyze that, what we should do is we should cook up a matrix, a 2x2 matrix, which encodes this quadric, whose entry here is r, corresponding to the x squared, whose entry here is s, corresponding to the y squared, and then these two entries have to add up to 1. And it's usual to make these entries symmetrically placed so that we get a symmetric matrix, so that would be a 1/2 plus and 1/2 there. So that's a 2x2 matrix that captures this quadric. And then to determine what kind of a quadric it is, the crucial thing to ask about this matrix is, what is its determinant? That's often the crucial question to ask about any matrix. And here the determinant is r times s minus 1/4. And the nature of the conic depends on whether that quantity is positive or negative. Okay? So if that's positive, then that's like the example of x, that's sort of like x squared plus y squared, like that kind of conic. That's going to be elliptic paraboloid. We'll talk about those more. On the other hand, if we have less than 0, then it's sort of like x squared minus y squared equals z. That's a hyperbolic paraboloid. That's more like a saddle shape. All right, so it looks like that curve, the curve RS equals 1/4 is also interesting. So let's graph x times y equals 1/4. Let's try that. Good, that's what we needed. All right, so there we have that of course is a hyperbola in the xy plane. Let's paint it something different. Let's say pink. I don't know. Style, how about a different style? Okay. There's the hyperbola. So what we're saying is that that's the place where the nature of the tangent conic changes. On the one side of that, on the positive side, when xy is bigger than 1/4, that means we're on this side of that branch or on this side of that branch there, then we should have elliptical kind of business. And in the intermediate region where the thing is negative, we should have saddle shape. So let's see if that actually corresponds. So you can see here in this range, we're getting, well, you don't see all the values because of the things, but it's all sort of elliptical, all the tangent conics. And then if we cross over here, we're getting these saddle-shaped kind of stories. Saddle shape. Until just here, you see we've crossed into the elliptical region. At this point here, we've actually in the hyperbolic region again. All right, so also notice that this xy equals 1/4 seems to very conveniently just touch the sort of central ellipse that I happened to draw there. I don't know if that's an accident or perhaps not. You can check whether that actually is a true tangency. All right, so that illustrates that we can try to visualize three-dimensional surfaces using GeoGebra. Gives you a little bit of experience with how to cook stuff up with GeoGebra. It's actually quite reasonable. Shows you also that you can use these sliders in a good way to move things around. All right, so that's good. We're going to talk more about quadrics later on. It's going to be very important for us. But in our next lecture, we're going to have just a very brief digression. We're going to talk about differential geometry over finite fields. So we'll see you then.